All right. Before I get too distracted, I do want to start day 21 because I want to see if I can get it done before I run out of time. I can go a little longer today. Normally I stop at 9, but I'm going to go a little longer today. I really want to get this done. Day 21, monkey math. The monkeys are back. You heard they're going to try to steal your stuff again, but it seems like they're just holding their ground and making various monkey noises at you. Eventually, one of the elephants realizes you don't speak monkey and comes over to interpret. As it turns out, they overheard you talking about trying to find the grove. Edible Monad, thank you for the raid. Much appreciated. Get Solid says, hi there, mind if I hang out? I promise I won't spoil. Yeah, feel free. And welcome. Thank you for joining the stream. As it turns out, they overheard you talking about trying to find the grove. They can show you a shortcut if you answer their riddle. Each monkey is given a job, either to yell a specific number or to yell the result of a math operation. All of the number-yelling monkeys know their number from the start. However, the math operation monkeys need to wait for 2 other monkeys to yell a number, and those 2 other monkeys might also be waiting on other monkeys. Your job is to work out the number of monkey named root will yell before the monkeys figure it out themselves. All right. Grab this as the test input. This seems like I don't want to build a tree. I mean, it seems like a tree would do it, right? You just build this tree of nodes and then evaluate the tree. But trees and Rust are if you don't need to, and I don't think we need to, if you don't need to, you shouldn't have to. I think I can just get away with a hash map. Because these are all just words, right? And we could just hash those. (22, 21). Yeah, tomorrow's going to be 22, 22. What did I mess up? Did I give something the wrong name? 22, 21, 22, 21. Oh, here it is. There it is. There we go. Okay, run. All right, so let's, I think the data is just a hash map of string to, what we can do is just create a monkey struct. Which is either a value, and we'll use our standard I64. Gaia 3V. Thank you for the sub. Oh, Edible Monad, sorry. Edible Monad, thank you for the gift subs to Gaia, to Cowface Dude, Trainerd, VMT TMV, who I haven't seen in a long time, and Hakuma Matata. That was very kind of you, Edible Monad. Much appreciated. Where are we going? All right, so we have the value, and then we have a binary op, which is going to take a string, an operation, and a string. And operation all right. Thank you again, Edible Monad, for that. Both for the raid and for the gift subs. So it looks like what it's just the 4 standard operators, plus, minus, divide, subtract, divide, multiply. I don't see anything here which enumerates them. Let's take a look at the test input. I mean the real input. There's 2,700 lines. Yeah, I'm just seeing pluses and minuses and divides. and multiplies. Okay, so let's just use those for the operations. I'm doing a lot of typing. For wanting to get through this quickly, I'm doing a lot of typing. All right, so I think that's it, right? The monkeys either produce a value or they ask other monkeys for values. Let's do this. Let lines is AOC lib read lines test input dot text, and we can do this. Oh right, we're going to build up this tree. Let's just do this real quick here. Duh. That was dumb. Okay. And this should be all the lines in the test input, which aren't that many. We're not using any of those things. Okay. Oh yeah, bacon's dumb about this. Okay. One of these days I'll hack bacon code. I've gotten more than my fair share of good use from it, so it's only fair that I contribute back, right? For line in lines, let left right is equal to, it's just the name colon something. So we can just do a split once. Unwrap. So the left is where we're going to insert, and the right has to get split again. If let OK and then num is equal to right dot parse I64, else do something else. And if it is okay, then we're going to say tree dot insert left dot toString comma monkey value no. Otherwise we'll say tree insert. Oh, we have to grab the left right, so let expr is equal to right dot split white space dot unwrap. That's unknown. I thought we could do a split white space. Couldn't we? Yeah, it's a split white space. Collect. Vec. Maybe. There we go. Now it's a vec of stir. So tree insert of left to string monkey binary. Let's see, it'll be expr of 0 dot toString operation parse, which I'll write in a second, expr of 1 dot chars dot next dot unwrap. This is terrible. And then expr of 2 dot toString. And then that's that. Then we'll say println. Oh, this has to be self tree. And then we'll debug out self tree. Right, parse doesn't exist, but I think we're close, right? So impl operation fn parse char self, and match ch is going to be a plus, is going to be self addition, minus is self subtraction. I probably shouldn't have called it something that big. Self multiplication, and slash is division, and everything else is just a panic of not an operator. Ch. Oops, gotta close that. Okay. I'm going really fast. I shouldn't be going this fast because I'm going to make mistakes. All right. I'm going to assume that's right. Maybe I shouldn't. Okay, let's take a look. Let's take a look here. DVPT is 3. LFQF is 4. LGVD is LJGN multiplication. PTHQ. All right. HMDT is 32. That's a big one. All right. But now it should be straightforward to evaluate this. I assume that's what we're trying to do, is evaluate it. Process continues until the root yells to number 152. Yeah, so all we have to do is evaluate. How hard could that be? Let's write an eval, which takes in a starting point, because we're going to do this recursively. Start, I'm going to take a reference to a string, and then what do we call the map? Let's just call it a tree. Hash map of string to monkey. And it's going to return an I64. Match tree dot get of start dot unwrap. We're going to assume that it's in there. This will blow up if it's not in there. So if it is a monkey value, then we're going to return B. That's a reference, right? Yeah. So we've got to return a copy of V. Monkey binary is where the fun happens. So it's going to be left, up, and right. So now we match on the op. Operation, addition, use operation. If it's addition, then we're going to return left plus right, right? Because these are I64s. Oh no, those are, sorry, those are not I64s. It's eval let left is equal to eval left tree. Let r equals eval right tree. So now it's left plus right. Subtraction is left minus right. Multiplication is left times right. And I assume this is integer division. We don't care about, or maybe the puzzle is set up such that whenever you divide, you're always going to divide a valid number or a multiple of the number you're dividing. Let's just throw it in there and see what happens. L/R. And that's all we care about. Two warnings, probably because we're not using eval. Yep. And then we just need to say eval root to string. This seems like a very simple part one, so I'm worried about part two now. Self tree. Is this, what was the answer for the test input? Oops. Such an ugly error message for you forgot an ampersand. 152, is that right? It's 152, look at that. Thank goodness. No more bots to worry about. All right, so now we'll use the real input. Oh, I shouldn't have printed it out, right? It's 27, yeah. Let's get rid of those lines. There we go. It ran quickly though, so that's the good news. It didn't take forever. Whoa, that's a big number. I'm glad I use I64s. That's the right answer. Huzzah! All right, let's go with Clippy. There we go. Well, one problem we haven't gotten this year, and I'm kind of disappointed, is a virtual machine kind of puzzle where you're given instructions and registers and you have to figure stuff out like that out. There's still 4 more days, so part 1. Code Monk says, good answer, well done. Get Salad says, now comes the fun part. All right, I'm looking forward to the fun part. What is part 2? Continue to part 2. Part 2 is, due to some kind of monkey-elephant-human mistranslation, you seem to have misunderstood a few key details about the riddle. First, you got the wrong job for the monkey named Root. Specifically, you got the wrong math operation. The correct operation for monkey Root should be equals, which means that it still listens for two numbers, but now it checks that the two numbers match. Second, you got the wrong monkey for the job starting with H-U-M-N. It isn't a monkey, it's you. Actually, you got the job wrong too. You need to figure out what number you need to yell so that Root's equality check passes. I'm just going to check. Ah, okay. I mean, they told me plus, so I didn't get it wrong. That's what I'm saying. The number appears after human in your input is now irrelevant. Okay, let's take a look what the number was. 557. In the above example, the number you need to yell to pass Root's equality test is 301. This causes Root to get the same number 150 from both of its monkeys. What number do you need to yell to pass Root's equality test? I'm guessing it's not 557. Wow. Okay. So how would we go about this? Let's go back to the running thing here. That evaluates very fast, doesn't it? One thing we could do, just as to start figuring out how to solve it, is to find the path to human. Which might be a little on the tricky side, but shouldn't be too tricky. We can start with the starting location, just like we did for eval, and our working tree, which is a hash map string to monkey still. And what we can return is whether or not we found a human down this particular branch. Option, a vec string. We'll make it references to strings so that way we can reference directly into the oops, that should be a colon. Oh, all right. It's saying add lifetime parameters. Okay, I can do that. That makes sense because it needs to know that the lifetime of what you're returning lives at least as long as the stuff you're working with. I have to add this here. Okay, so that builds. Let's see. In order to see if we found the human branch of the tree. All right, first let's switch back to our test input before we do anything else. And now what we can do is first our ending condition, our finish condition is if lock is equal to human, right? H-U-M-N. I think I can do that comparison, right? An ampersand stir with an ampersand string. That works. So we return some vec bang of human. If we haven't found the human, then we want to see, are we working with a binary operation? If let sum monkey binary left operation and right is equal to tree get location. Then we can look down the left branch and we can look down the right branch. And in order to look down the left branch, we can just say if let sum vec is equal to find human left tree. Then we found it, and what we want to do is, we want to add ourselves to it. So we just want to say vec push lock and then return some vec. In order to do that, we have to make this mutable. All right, we get back a mutable vector, and then, or we get back a vector that's ours, and then we say that we want to be able to mutate it. Otherwise, we'll do the right branch. Change the L to an R, and we do that. That's all we need to do there. If we found a value, then obviously we're not a human, so none. Is that all we need to do to find a... Okay, let's see. Let me print that out as part 2. Println. Debug out. Oops. Find human. Starting at root to string of self tree. All right, and that okay, so I think it found a path to human, right? It went root to here, to here, to here, to here, to here. And now we just need to figure out what to do. Now that we have that information. So we can evaluate from root, we can evaluate the 2 halves of its tree. Right? We can say let root is equal to self tree get root to string. Let me make one of those. Let root name. Yeah, let's just call it root name is root to string. That'll save me a little bit of typing here. Root, and let's call this root node. Unwrap. Okay. So this is a monkey. So now what we can do is evaluate the 2 sides of the tree, right? And we can just compare them. Print, then left is equal to this, and right is equal to this. And we can say eval root node. Oh, this is a monkey. Yeah, we need to destructure it. Monkey binary. Left, up, right. So we're going to do left self tree and eval right self tree. I think this is going to end up being a recursive solution. Also, we're going to walk our way down. Oh, we can't do that? Oh, this is neat. I didn't realize that. Okay, left right equals if let else something. Do I need an else condition in there? Else to do. Else panic. Root monkey has no data. Something like that. Pizza. Thank you for the follow. Much appreciated. Okay, so now left and right need to be strings. And now it doesn't like this again. Expected enum option found enum monkey. Yeah, okay. I'm sure there's a way to do this. Match. Monkey. Val. This is the panic. And then monkey binary. Left. Op. Right is left right. This is let left right equals. That's too bad that the if if let doesn't work. Oh, it's value. It still doesn't like that because I didn't do an unwrap. We finally have it. Oh, good. Okay. So now we can see that the left is 2 and the right is 50. So the question is, do we go down the left node or the right node? Right? And we know which one we need to go down because we have the path. Right? We found the path to the human. Let path equals find human. So now we just need, actually we need to reverse it because we want to walk backwards. Let path equals path iter reverse collect. And then we want to walk our way down. Oh, okay. So we have left and right. Let's say we need this to be if left is equal to path of 1. I'm just right now I'm just hacking. I don't have an answer yet. Then we're going to eval the right side. Let wrong num. No, right num is equal to this. Else. So did we properly figure out the correct number? So it should be 150, and the wrong number is 2. So println, I did something wrong here though that it doesn't like. All right, we'll figure it out when we hit the compiler. The correct side is right num. Let's see if I got this right. Oh, because I put a paren there. I didn't even see that. Okay, now we can't compare this. Wait, path is supposed to be a vec of, oh, okay, let's do unwrap. That's what happened there. Vec of ampersand string. There we go, vec of ampersand string, okay. So the correct side is 150. So that means we have to go down the wrong, quote unquote, wrong side and fix it. Okay. So I think that gives us enough to work with, right? We just need to create a function, which gives us the answer, right? Find adjustment. We have the path. Path is a vec, right? Yeah, then I want to pass in an ampersand. I want to pass in a reference because this is going to be a recursive one. Our starting point is path of 1. And every time we call it, we're going to work our way down the path. We have our tree that we need to work with and the value we're looking for. I don't want to call it right num because we have left and right. Correct val. Right? So this is all we need to do. Super simple. Is find this correct val. And then as we walk down the tree, we can look at what the correct val should be for that and then take the branch that the human is on. I think that'll do the trick. Let's see. So find adjustment is just takes a path with the vec of string and then index into the path. There our tree, which is hash map string monkey, and then the correct value, which is an I64. I'll just call it CV. And it's going to return I64, which is going to be the adjustment we need to make in order to get the thing to work. Hirschema, thank you for the follow. Much appreciated. Okay, So now we're at some node, right? If we're at, let's say match tree.get, whatever path index we're on, we're going to try to look up what the value should be. If we're at monkey value of v, that means we found the human, right? We made it all the way down the human path, and we actually have the value we're supposed to be giving. So it should be the correct value instead of whatever value this is. Oops. Sorry about the jumping around. If it's a monkey binary operation, we have a left, an operation, and a right. We need to solve the left and right and then figure out what we should adjust based on the next path in the index. And then use that, whatever that value should be, as our next value to use for the level down the tree, right? Because as we work down our tree, we actually have to undo the operations. And this is where I'm a little nervous, because we're doing left divided by right, and if that can lose information, right? And in order to reverse a multiplication, you need to do division. All right, let's just figure it out. We know we can evaluate the left and right sides. Right? So now we have two numbers for left and right. And now we have to see if, oh, we don't want to lose left. Let's just call it left and right, because we actually need to compare the strings. Okay, if L is equal to path index plus 1, right? In other words, the human is down the left path. That means the human has the wrong number, and we need to figure out what the correct number is. So match operation. And I'm going to use operation star again here, so I don't have to type so much. If it is addition, now we have to figure out what we need to do. Okay, so let's figure this out. So left plus right is equal to some value. Needs to be let's see, equals CV, right? And then I can do the same thing for the other operations. Having it here in my head rather than in my head will make it easier for me to figure out. We're trying to get the left side to be the correct value here, and it's the wrong value. So for addition, it's going to be the correct value minus right, right? We just move right over there. CV minus right. For subtraction, oh, I got these in the wrong order. It's going to be CV plus right. Doesn't matter the order. Multiplication. Right, so this is where we say CV divided by right. And division. I misspelled that. And now we just multiply both sides by right times right. We can actually just return that, right? We can say let new CV. Else, we assume that right is equal to path index plus 1. So we're going down the other path, match op. And it's going to be slightly similar, but very different. Now it's the left side we have to do. We have to move. So we have to say right equals, yeah, so that's easy. It's enough CV minus left. For subtraction, we can't just move that over because then we'll have negative. So we add both right to both sides to subtract CV. Okay, so this would be left minus CV. For this one, it's just division, right? It's just CV divided by left. And then division, this is in the denominator. So we have to multiply both sides by right, and then we have left equals CV times right. But then we want to divide, okay. So it's left divided by CV. Wow, okay. That one's a weird one. These are all very nice. It was, you know, just opposite operator. But if you're doing the other side, they alternate which goes on which side. And then this ends up being two division. Is that right? We don't have to do a multiplication anywhere because we need to divide CV left by CV in order to get right. All right, and then once we have that, that's our new CV. That's the new value we want for the next path down. So we're going to return find adjustment of our current path, the next index in that path. We'll just pass the tree down, and the new value that we're looking for. And then see if that builds. Of course it doesn't. Oh, this needs a this. All right. Expected struct string found ampersand string. Oh, okay. Oh, this probably, are we going to have to play around with lifetimes again? Oh, that built. And it came up with 301, so you can't argue with that. Right? That was what they said, 301. All right. Should we try the real input? And the real number is something big, which if I got wrong is going to make me cry. And fortunately, I don't need to cry. Yay! All right, I managed to get all caught up. How'd we do? Ooh, that's good. Cracked the 10K mark again. Get Salad says, beautiful solution first try. Yeah. I mean, wasn't, once I was able to reason out what needed to happen, it took me a while to get to this point, right? Figuring out how to do the path, and then figuring out how to determine which side was the wrong side, and then, yeah, and that's basically the same logic. I bet you we could simplify it some, because I have this basically here and here, sort of, although this doesn't need this needs an equality check. So we could add an equality check and then put an equality check in here and then do the same thing.